Today we are starting Trig. Yay! Before we actually get into it, there's one important note I want to tell you. You might remember this from your geometry classes, but if not, that's okay. When we talk about triangles, which we'll do for the next few lessons, anytime we label a triangle, the angles are always going to be capital. And the sides are always going to be lowercase. And in addition to that, whatever we call an angle in a triangle, A, B, C, it doesn't have to be A, B, C, call it D, E, F if you're feeling crazy. The side across from an angle should be named with the lowercase version of that letter. There are times when this won't be possible, and that's not a big deal, but whenever possible, if an angle, you know what, just because you're used to seeing the C at the right angle, I'll call this one B. And whenever the angle is uppercase B, the side across from it is lowercase b. That's an important little feature we use when we name triangles. Okay, today we're going to be talking specifically about right triangles. And what we're going to do is build this chart, and a lot of this is from the video notes, where you will have a chart that tells us if you're given specific measurements and we're looking for something else, we'll figure out how to solve it. First one I'll start with is easy. Anytime you are given two angles, and we want to find the third angle, you always subtract the two angles from 180 degrees. Always. Now, if one of those angles is a right triangle, you can just subtract the second one from 90 degrees. That's the first one. Then we get into some of the right triangle specific stuff. If we look at number 2 here, notice we're not talking about angles yet. We're given two sides, and we're looking for the third side. Hopefully you guys remember this one from your geometry classes and also from, some of the math classes you took before that. There's this fancy little thing called the Pythagorean Theorem, which tells us that the sum of the squares of the legs of a right triangle equals the square of the hypotenuse. And no matter where that unknown piece is, whether it's one of the legs or whether it's the hypotenuse, you'll always end up with an equation that's pretty easy to solve. So x squared plus 49 equals 225. It is worth memorizing your perfect squares, at least through like 16 squared. There's 256. And if we subtract 49 from both sides, 225 minus 49 is 176. And so x, that missing leg, would be the square root of 176. Unfortunately, 176 is not a perfect square, but 16 does go into it 11 times. So I can write this as 4 root 11, and that would be the missing side. So this goes right onto our chart. Our second possibility, another pretty easy one. If we're given two sides in a right triangle, and this only works for a right triangle, and we're looking for the third side, we can always use the Pythagorean theorem. And then if we're missing one of the sides, and we're given the right angle, another angle, and one of the sides, it doesn't matter which one we're given, we can use what you learned about in the videos, SOHCAHTOA, the definitions of sine, cosine, and tangent, to find the missing side. So here's how this one works. If I'm looking for side y right here, and I know that this is a 30-degree angle, what I can say is that the definition of cosine Cosine is the ratio of the adjacent leg to an angle over the hypotenuse. That's what cosine measures. It measures how big this side is going to be compared to that side. The cosine of every 30-degree angle is always going to be the same. So I can say that the cosine of 30 degrees, that ratio, is equal to y over 8. And from there, once I have the equation written down, I'll just solve it however I can. A lot of students find it useful to put the over 1 here, so you can cross multiply. If you don't need the over 1, don't worry about it, it's not important. So we cross multiply here, 8 times the cosine of 30 degrees. Notice how I cannot multiply the 8 and the 30 degrees. Also notice I'm going to keep writing that degree symbol. That is equal to y. And you know what? That is something which I'm going to put into a calculator. Later on, we'll learn how to know some of the angles without using the calculator. We're not up to that quite yet. I do want you to notice that your calculators, as well as Desmos, when you just type in the cosine of 30, it doesn't know you mean 30 degrees. We have to specifically tell Desmos that every time. And the way we can do that is in the graph settings. We can just click on this degrees button down here. And now it knows that anytime I use the cosine or sine or tangent, I'm talking about degrees. So 6.928. Usually when we're doing this, we can say that the angles, usually we round to the nearest tenth. So 6.928, I'll just call that 6.9. One thing worth noting is if the piece of the triangle we're looking for is in the denominator of the fraction, the denominator of the ratio we use, like in number 4, I'm going to use tangent of 27 degrees because the two sides I have to work with are the leg opposite the tangent, the 27 degree angle, and the leg adjacent to the 27 degree angle. And the ratio of the opposite leg to the adjacent leg is 9 over x. I'm still just solving for x. This one, the one might be more useful to you. If you kind of see the cross multiplying here, you multiply x times the tangent of 27 degrees equals 9 times 1. So then you look at that and say, oh, well, if I just want to get x by itself, we've done this in like all of our recent units, whatever is next to x, I can just divide by it on both sides. X divided by the tangent of 27 degrees. And again, you're not supposed to know that off the top of your head. There's no way to calculate that by hand. We'll just type that in. 9 divided by the tangent of 27 degrees. That's 17.7. And so what I can do is go back to my chart and say, in this chart, if what you are given is one angle and one side of a right triangle, so that means we also have to be given 90-degree angle, you know where that is. And what we're looking for is another side. The equation we will set up is either the sine of the angle equals the opposite over the hypotenuse, or the cosine of the angle equals the adjacent over the hypotenuse, or the tangent of the angle equals the opposite over the adjacent. So I'll just write SOHCAHTOA, TOA, which is the mnemonic we use to remember which side goes with which. The sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. And then the last possibility here for finding a missing piece, finding the missing measurement of a right triangle, is if you're missing the actual angle itself. This one was not in the videos for yesterday. But in this case, we are given the sides of the right triangle, but not the the angle. We do need to know where the 90-degree angle is, but we're not given the others. For this one, we're going to use the same SOHCAHTOA. And in this case, because I know all three sides, I can actually use whichever one I want. I haven't used sine yet. We used cosine, we used tangent, so let's go with sine. The sine of that x degree angle is equal to the opposite leg, 12, divided by the hypotenuse, that's 13. The sine of some angle x is equal to 12 over 13. Now, to answer this question, we need to think back to what we did with exponentials, what we did with squares and with cubes. For every one of these functions, if we want to undo it, we used its inverse, right? The inverse of an exponential was a log, so if we wanted to undo 2 to the x, we used log base 2. So what we need is the inverse of sine, the function, so that, let me back up a step. If we take an angle and plug it into the sine function, by the way, sine is spelled S-I-N-E, even though its symbol is just S-I-N. And what comes out of that is some decimal. We'll talk more about this in the coming weeks, or right after spring break. But because the sine is the leg divided by the hypotenuse, it's always less than 1. The idea of the inverse is we want a machine, and we've seen this diagram before. We call this inverse sine, and there's another name I'll give you for it in a minute, where if we take the decimal and put it into the inverse sine, we'll get the angle out. And so that's what we need here. We need a machine so that if we put the 12/13 into the machine, the angle whose sine is 12/13 will come out as the result. The name of that machine is inverse sine, which is written in 2 ways. I recommend you use this way. It's called arc sine. Arc sine of 12/13 is equal to x. That's this function right here. It's called the arc sine. If you go to your calculator and you type in arc sine, watch what happens to the font, by the way. It knows that that's a function. It turns it into non-italicized. If I put in the 12/13, it tells me the angle whose sine is 12/13. So this is about a 67-degree angle. By the way, usually when we're talking about angles, we round to the nearest degree, not a decimal. So that would be the answer there. X is 63-degree angle. Now, so what we'll do is we'll go back to our chart, and we'll add that as the final row here on our chart. If we are given, remember this is still in a right triangle, so we're still given the 90-degree angle and any 2 sides. First of all, we already know we can find the third side with the Pythagorean theorem, but we don't even need to if all we're looking for is one angle. We will use the inverse trig. Inverse sine, inverse cosine, inverse tangent. They'll all work. It just depends on which sides you want to use. I did promise you I would tell you the other notation for inverse trig. I recommend you use arc sine of x, but the other way to write it is using that inverse notation we learned about in the beginning of last unit, which is that little -1 in what looks like an exponent, but is absolutely not an exponent. We read that as inverse sine of x. We do not read that as sine to the anything. We'll talk more about that in the coming weeks, but right now we would never call that an exponent. That is the inverse sine of x. So these are 2 ways of writing inverse sine of x.